The choking agent phosgene was responsible for at least 80% of the deaths due to poison gas in World War I. Like chlorine gas, the other major choking agent used during the war, it reacts with the water in the eyes, the sinuses, and the lungs to produce hydrochloric acid. Phosgene is slower acting and more insidious than chlorine gas, but just as effective at destroying respiratory tissues. Diphosgene is a related next-generation agent. Where phosgene is a gas at room temperature, diphosgene is a liquid, making it easier to handle and store. More importantly for our purposes, its breakdown products were designed to attack the filter cartridge as well as the soldier that was depending on that cartridge for their own protection. A significant contribution that we can make to chemical warfare defense and prohibition enforcement is the ability to identify trace amounts of an agent after a suspected attack. This allows us to confirm the nature and the extent of the attack so that we can provide evidence-based recommendations for victim treatment, for decontamination procedures, and other measures for public safety. Some elemental analysis methods like flash combustion and gas chromatography can tell us the ratios of elements in a compound, but not how many atoms of each there are or how they connect to each other. That takes our scientific expertise to piece those molecules back together and see what they were to begin with. Let's use diphosgene as an example. Elemental analysis shows that an unknown sample contains 12.4 mass percent of carbon, 16.18 mass percent of oxygen, and 71.68 mass percent of chlorine. Using that information, we can determine the empirical formula of the unknown sample. So 12.14% carbon divided by the molar mass of carbon, 12.011 grams per mole, gives us 1 part of carbon. 16.8% oxygen divided by the molar mass of oxygen also gives us 1 part of oxygen. And 71.68% chlorine divided by the molar mass of chlorine, 35.45 grams per mole, gives us 2 parts of chlorine. So that's everything we know that's in this compound, 4 parts in total. So we have 1 part carbon in 4, 1 part oxygen in 4, and 2 parts in 4 of chlorine. This gives us the empirical formula of COCl2, which is actually the molecular formula of phosgene. So to determine whether or not this is phosgene or diphosgene, we would have to rule out the lower total molar mass of the compound with some complementary method like mass spectrometry that would tell us the total molar mass of the parent molecule. If we determine that the total molar mass is 197.82 grams per mole, now we can use that to determine the molecular formula. The molar mass of COCl2 is 98.91 grams per mole, so we know that this isn't phosgene. Multiplying everything by a factor keeps the mass percentages the same, so let's try doubling it to C2O2Cl4, the molecular formula of diphosgene. That gives us a molecular weight of 197.82 grams per mole, which matches our experimental data.